Hi everybody. In this video we are going to discuss stability in the frequency domain. First of all, let's listen to this. Well, bloody hell. This is what we call... Hello? Well, I put it away. Whoa. This is what we call audio feedback, oscillation in the frequency domain. And that is because we have a system which starts to oscillate, in this situation with a speaker and a microphone. So now let's look to a control system, because in that control system the same thing can happen. In this control system we have two transfer functions, one in the straightforward line and one in the feedback loop, H1, H2. So we can say that the transfer function, the closed loop transfer function from output Y to input X is equal to all the blocks in the forward path H1 divided by 1 plus all the blocks in the loop, 1 plus H1 times H2. Well, this system starts to oscillate when all the blocks in the loop, so what we call HL, all the loop blocks, are equal to -1. That is what we call the oscillation condition, and that is what happened in the audio feedback, what you heard before. So we have to judge whether this can occur. Is there a frequency at which this condition will be violated, or I should say will be met, because in that situation we have oscillation, and that is of course what we do not want. And what we certainly do not want is that at a frequency of minus 180 degrees, the amplitude of all the blocks in my loop is not equal to 1, but is equal to a larger value than 1, because in that situation we are simply unstable. So we have to look to the open loop system, the loop system, and we have to judge whether the phase of this system, HL, which is equal to H1 times H2, whether this phase will be minus 180 degrees or not. And when it is the case, we have to look to the amplitude of the gain of the combined blocks in the loop. And when that gain is larger than 1, we are unstable. That's the condition to check stability in a frequency domain. So again, we have to check this condition, and we can do that in Bode plots or in our Nyquist plot. And stability requirement, this has to be met in all situations, so for all frequencies. So when there is a frequency when this condition is true, so at 180 degrees, a phase of minus 180 degrees, the amplitude of everything in the loop is higher than 1, then we are unstable. So first of all, let's look to an example over here. Suppose that HL, so the combination of all the blocks in the loop, has this transfer function. And we are going to look to the same situation where we have the same transfer function, only the gain is lower. Well, first of all, let's look to the phase plot. This is a third order system. So that third order system can have at the end, at very high values of omega, a phase of minus 270 degrees. And remember, the phase for both systems is the same, because it's minus 3 times the arctangent of omega times 2 divided by 1. So that phase crosses the minus 180 degrees line. So at that value of omega, we have to look whether or not the amplitude has an amplitude of value of higher or lower than 1, which is 0 dBs in the Bode amplitude plot. So for the green condition, we see that the amplitude is lower than 0 dB, so the amplitude is lower than 1 for this frequency. And for this situation, for this system, at the same omega, the amplitude is higher than 0 dB, so the amplitude is higher than 1. So this system is unstable because the amplitude at the point where the phase crosses the minus 180 degrees line is larger than 1, and in this situation for the green system this system is stable because here the amplitude is lower than 1. Okay, that's the stability criterion seen from a Bode plot perspective. Now let's look to Nyquist. Also, using the Nyquist plot, we can judge stability. In this situation, we have a first order system. We can see it over here. Transfer function is 1 over 1 plus j omega times tau. So this is what we call the Nyquist plot of that first order system. And we see it starts off over here at omega is 0 and it ends up over here in omega is infinity. Well, what we know from a first order system is that the maximum phase shift at very high frequencies is minus 90 degrees. So in this situation, we never reach a phase of minus 180 degrees. So the minus 180 condition is never exceeded, so the phase is never exceeded, so this system is stable for all values of omega. So it's always stable. First order system, purely first order system is always stable. Now let's look to a second order system. And a second order system has a more or less equal Nyquist plot, only it has a maximum phase shift of minus 180 degrees for high frequencies. So for omega is infinite values, it has a very high value going to infinity. My Nyquist plot goes to the origin over here. So in this situation, my amplitude is 0 and my phase is minus 180 degrees. So it never crosses that minus 100 degrees. And you see that the amplitude is almost 0. So also a second order system is always stable. When you have a pure second order system, it's always stable. So here it ends in the origin. So now let's look to a third order system. And for a third order system, we know that the phase ends up in minus 270 degrees for high frequencies. And so it crosses that minus 180 degrees line in all cases. So at a certain frequency, we cross that minus 180 degrees phase. It crosses over here. So at that point, we have to judge whether the amplitude is higher than 1 or not. And in this case, that amplitude over here has a larger value than 1. So in this case, we cross the minus 180 degrees line with an amplitude which is larger than 1. So this system is unstable. So what we can conclude until now is that from third order processes on, instability can occur because a phase shift of minus 180 degrees is possible, so we have to judge whether or not at that point the gain is higher than 1 or not. And when it is, you should design your controller in a way that the value, the maximum amplitude at that value at that omega value where the phase is minus 100 degrees is never larger than 1. So you can do that, for instance, by decreasing your proportional gain, or you can add a D action to your controller because that gives an extra phase shift of plus 90 degrees. Well, this is an important one. Watch out for delays in your open loop system because a delay transfer function looks like this. It's e power e to the power minus j times omega times the delay times td. And this is an exponential notation of a complex number in which this is the amplitude, 1, and the phase is everything which is in the exponent over here except for the j. So the phase of this system is minus omega times td. So this system and delay will always cross minus 180 degrees because when the omega increases, that argument, that phase will get lower and lower and lower and lower, and in the end it will always cross minus 180 degrees. Okay, my amplitude is 1, but when a delay is added to my system, it could cause instability because due to that delay, due to that extra phase shift, we always cross that minus 180 degrees line. So you have to judge stability in all systems in which a delay has been implemented. And The problem is that in digitally controlled systems, we have always delays because there is delay due to the sample time. So in digital systems, you have to judge stability in all situations. Well, we have looked to stability in the Nyquist situation, so we're looking to a Nyquist plot. And we can look from another perspective to stability in a Nyquist plot. What we can also say is that when we travel on the Nyquist plot of that open loop system from omega is 0 to omega is infinity, you check if the point -1 is at the left side of the curve. And when that is the situation, in that case, my closed loop system is stable. That's another way of looking to stability in the Nyquist plot. We're going to do this in a couple of examples. In this example, this is my Nyquist plot. And we travel on that Nyquist plot starting at this point where omega is 0 towards omega is infinity. And when we do that, we see that the point -1 is to the left of this curve, so this system is stable. And we will, of course, know that because we can also say that this system never crosses the -180 degrees line, only in omega s infinity, so that is not the case in real practice. Now let's look to this system. When we travel again on a Nyquist plot, we travel from omega is 0 to omega is infinity, and we are going to the origin over here, and we cross the -180 degrees line, but we see that the point -1 is to the right of the curve. So we know in that situation, because the point -1 is to the right of the curve, this system is unstable. We can also say, well, at -180 degrees, the maximum amplitude is higher than 1, so we are unstable. This system also traveling from omega is 0 to omega is infinity, and we see that the point -1 is to the left of the curve, so this system is stable again. Again, because at -180 degrees the gain is lower than 1, and this system is of course unstable because the point -1 is to the right of this curve, which can also be seen because at the phase shift of -180 degrees, the gain is larger than 1. Okay, that was about stability. So summarize, the closed loop system is stable if the open loop conditions are matched, which say that at a phase shift of -180 degrees, so when I cross that phase, -180 degrees, you have to check the open loop gain, and when it's lower than 1, your system is stable. And you can see it in a Nyquist plot from traveling to omega is 0 to omega is infinity, and then for a stable signal, the point -1 should be to the left of the curve. So we have seen so far that we can define stability, but in practice we have to add margins to that stability, because in practical situations, first of all, you do not know exactly how your system looks like when you make a model out of it. Secondly, you could have tolerances in your system, but also your parameters may drift. So we have to take stability margins into account. And we define two stability margins. And one of them is the gain margin, and one of them is the phase margin. Phase margin and gain margin are defined as follows. The phase margin indicates how much the phase may decrease when the gain is 1 before it reaches -180 degrees. Well, how does that look like in a Nyquist plot? This is my Nyquist curve over here, and I've drawn a circle with an amplitude with a radius of 1 over here. And for the phase margin, we look to the point where my amplitude is equal to 1, and that is over here. And then we see that we have left so much degrees, and that is what we call the phase margin. So in this example, the phase margin is almost 75 to 80 degrees. So for the phase margin, look to the point where the amplitude of your open loop system, which is the red curve, is equal to 1, and then see how much phase is left before you reach -180 degrees. And in practice, a phase margin of 45 degrees is really good value to start with. Then let's look to the gain margin. And the gain margin it indicates how much the gain of an open loop system may be increased when the phase is minus 180 degree before the gain is equal to 1. So in this situation, we look to the Nyquist curve over here, and we look to the frequency here where my phase is minus 180 degrees. And you see that, well, in practice, this is about a gain of about 0.5. So in this case, my gain may be amplified with a factor of 2, 1 over 0.5, in order before we get unstable. So in this example, my gain margin, which is a good margin to start with, is 2. So in general, when this is B, then my gain margin is equal to 1 over B, because when I multiply B with 1 over B, then I have a gain of 1 and I start to oscillate. So again, the gain margin, look to the phase of minus 180 degrees, and when that is the case, see how much your gain may be amplified before you get a gain of 1. And in practice, both requirements have to be met to guarantee a robust system stability. Well, that was from looking to a Nyquist perspective. We can also judge these phase margin and gain margin from a Bode plot, and then it looks like this. This is my phase characteristic, and this is my amplitude or my gain. And remember, in the Bode plot, it is in dB. So the phase margin, for the phase margin, we look to the crossing of that amplitude plot. We look to the crossing with the 0 dB line, because 0 dB is equal to a gain of 1. And then we see that there is this much of a phase margin left before we come to a phase of minus 180 degrees. So this is my phase margin. And for the gain margin, we look to the point where the phase crosses the minus 180 degrees line. Of course, that is equal to minus p radians. And then we see how much gain is left before we reach the 0 dB line, which equals a gain of 1. Well, that is all about stability in the frequency domain. Thank you again for watching.